Now, let's begin with the first order features. First order features focus on the distribution of intensity values without considering the spatial relationships or patterns between the different pixels, making them first order. So the complexity of it is now just a first order because you are dealing with the same pixel. No relationships between the pixel and the neighbors. They represent the simplest and the most basic statistical measures derived directly from the pixel intensity values within the ROI. There are many first order features such as mean or average, variance, skewness, kurtosis, and entropy. The purpose of the first order features, they give insights on the texture and intensity distribution of the image. For example, you can get the overall brightness or the shape of the intensity histogram. The first feature is called mean, and simply it is average gray level intensity across all of the pixels in the image. Simply, you sum all of the pixels and divide it by the number of pixels, then you will get average. You can use the mean to indicate the overall brightness or darkness of the image. A higher mean means a brighter image, while a lower mean indicates a darker image. The second is standard deviation, and it measures the spread or variability in the pixel intensities around the mean. A high standard deviation indicates a large or wide range of intensity values, and we can call it high contrast, and a lower standard deviation means a uniformity or low contrast. The third is entropy, and here we quantify the randomness or unpredictability of pixel intensities, and if you get a high entropy value, then this indicates a more complex and textured image, while low entropy means uniformity and simplicity. Skewness, here we need to measure the asymmetry of the intensity or probability distribution around the mean, and the asymmetry here means simply we need to indicate whether the samples or observation are concentrated on one side over the other. So it's symmetrical if the skewness is 0, and if we have a positive skewness, then this means that the distribution is right skewed. And if it's negatively skewed or a negative value in the skewness, then the distribution is skewed to the left. And the direction here, left and right, is opposite to you. So if you are looking in the direction, then this is your left and this is your right. The distribution skewness here is the opposite. Here is the right and here is the left. Kurtosis is another feature, and here we need to describe the shape of the intensity distribution, or simply we can call it the degree of tildness. If we have a high kurtosis, then we have a sharp peak, and if we have low kurtosis, we have lateral distribution. Then there is another feature called excess kurtosis, and it's similar to the kurtosis value, but you subtract 3 from it. So if the kurtosis is 40, then the excess kurtosis, subtract 3 from it, it would be 37. And based on the excess kurtosis, if it's positive or greater than 0, then you have sharp peaks, and in this case we can call it leptokurtic distribution. And if the excess kurtosis is 0, then it's a normal distribution, and we can call it mesokurtic distribution. And if it's negative or lower than 0, then we have lateral distribution, and we can call it platykurtic distribution. So using the skewness and the kurtosis, we can determine the symmetry and tildness of the distribution. And these are the different formulas to calculate the different features. Simply, for the mean, you are looping on all of the pixels, summing them together, and dividing by the width multiplied by height, or the number of pixels in width and height. There is another and better approach than this one, and also faster, that we are going to discuss it later using the histogram. But first, let's interpret the features. If you have high mean, then you have a bright image, and a low mean means a dark image. And if you have high standard deviation, then you have high contrast, and if you have low value, you have low contrast. If you have high entropy, then there is a complex texture, or there is randomness in the ROI, and if you have low entropy, then it's uniform or a simple texture. For skewness, if it's targeted to the right with a high value in the skewness, then there are more bright pixels. and the opposite for low value skewness. For kurtosis and excess kurtosis, if you have a high value, then you have sharp peaks and you may have outliers. And for low value kurtosis, then you have flat distribution and few outliers. So simply you understand the meaning behind each of them and how to interpret the value that you gained. So assume that you are differentiating between tumor A and tumor B. And let's assume that you got a mean here with 100 and you got a mean here with 25. Then simply you can say I can discriminate them using the mean value. For tumor A, you can determine that it's a tumor with type A because it's a bright image or high mean, and the opposite for tumor B. Maybe you can also use kurtosis. If you visualize tumor A, you may find it like that. For tumor B, you may find it like that. So by plotting the histogram and the distribution of the data, by looking through the distribution or the kurtosis values or the excess kurtosis values, you can say this is tumor A and this tumor B, because tumor A has the theme of containing sharp peaks and tumor B has a theme of being flat. Now let's understand how to calculate the different features using the histogram. Simply, a histogram means we need to create a plot that consists of the pixel values and the corresponding frequency. So as a whole measures or describes the distribution of the image or the matrix. So simply to create the histogram of an image, you put the pixel values in the x coordinates or horizontally. We have here 5 unique values, 1 to 5. So we will put 1, 2 until we reach 5. And for each pixel value, we count the frequency or the occurrence of that pixel. So at 1, we have 1, 2, 4, 6. So we create a bar chart or we put here a point at 6. For pixel 2, we have 1, 2, 4, 6, 7, 8. So we put here a value 8. And the same for others. By plotting that, we now have the distribution and we can easily calculate the different features based on that histogram. First, we can determine the minimum, maximum, and range, the count and the sum. The minimum here is 1, the maximum is 5, and we can use these two values also as features. The range is from 1 to 5. The count is the number of pixels, which we know here is 5 by 5 is 25. And to determine the count from the histogram, simply count the occurrences. 6 plus 8 plus 3 plus 5 plus 3. So we have 25. And to calculate the sum using the histogram, simply multiply the pixel value by its corresponding occurrence. So simply 1 multiplied by 6, 2 multiplied by 8, 3 multiplied by 3, 4 multiplied by 5, 5 multiplied by 3, so the total sum is 66. Then you can determine the mean by dividing 66 by 25, the sum by the count. So it's 2.64. And the variance, which we can use it later to get the standard deviation, is simply subtracting the pixel value by the mean, then square that value and multiply it by its occurrence. Do that for all of the values and divide it by the count. So simply 1 minus 2.64, all of that squared multiplied by 6. Then 2 subtracted from 2.64 squared multiplied by 8. And the same for the rest. Divided by 25, you will get 1.8 as a variance. Square it, you will get the standard deviation. The skewness and the kurtosis are similar to the variance, but instead of using power of 2, in skewness you use power of 3, and kurtosis you use power of 4. And for the denominator, instead of dividing by 25, you are dividing by 25 multiplied by the standard deviation raised to the power of 3 in skewness, and here is to the power of 4 in kurtosis. And for the excess kurtosis, you get the kurtosis and subtract it from 3, you get the excess kurtosis. So simply, the equation of variance, skewness, kurtosis look the same. Get count sum to get the mean, get the variance to get the standard deviation, get the kurtosis to get the excess kurtosis. Based on these values, we can analyze and interpret the results. We have negative excess kurtosis, and this means we have a flatter distribution. We got a positive skewness, so it's right skewed, and the skewness is a small value, so we can say it's a slightly right skewed. Now it's your turn. You can pause the video and try to calculate the different features for this matrix. The difference between this matrix and the previous one is that I changed 1 to 5s here. After it determines the features, there's a final result. If you notice, the skewness here, it changed to negative, and this means it's left skewed. Also, the excess kurtosis remains negative, and this means it remains flatter. So simply, if you have the tumor A has a positive skewness like here, and the tumor B is a negative skewness like here, then you can simply say, I can interpret from the distribution whether it's tumor A or tumor B from the skewness, or the variance, or the excess kurtosis, and so on. Now, we need to apply that using code. Go to the third code, first order features example. At the beginning, we imported NumPy and matplotlib for NumPy for numerical operations and plot or matplotlib for plotting, because we need to plot the histogram at the end. We defined a NumPy array with a type unsigned 8-bit integers. So each value here will be stored in 8-bit and it's integer and unsigned. So there are no signs here. There is no negative values. And the reason that we use NumPy here is that it will be simpler to apply operations and the numerical operations on the array here. We defined the same array similar to our example. Then we started to find the minimum and the maximum. Here is the minimum using the min function and maximum using max function. To create the histogram, we created a vector or an empty list called hist2d, histogram to dimension, and we went through each possible value in the range from minimum to maximum. As we mentioned, we got a range from the minimum to maximum, and that range will be plotted or added to the x-axis in our example from 1 to 5, and we added +1 here because the range is exclusive, so it starts from the minimum and ends before the second value, which is maximum +1, so it should end at max. For each value which is stored in the counter I, we need to check the count or the occurrence of non-zero pixels. For example, it will start at pixel 1, so I need to count the corresponding frequency to 1, and the same for 2, and the same for others. Append that into the histogram, and after that, convert it to a NumPy array. Again, we here use a NumPy array because it's easier in the mathematical operations. So this array should store the frequency. If we return to our example, the hist2d should contain the values 6, 8, 3, 5, and 3. Now I need to count them, so I use the sum function to count or to sum the values of the frequencies in the histogram. Now we have the count, we have the range, minimum to maximum +1. We have the sum by simply multiplying the histogram by the corresponding range. So it will start to multiply the first value by the corresponding one, the second by the corresponding one, and so on. And finally, apply the summation to the result vector to get a singular value. Divide the sum by the count to get the mean. Then to get the variance, subtract the mean from the range, which is the horizontal axis, square it, and multiply it by the frequency, which is the histogram, and then sum it together and divide by the count. Then you have the variance. Apply the square root, you can get the standard deviation. Do the same to get the skewness and the kurtosis. Instead of 2, use 3 in skewness and 4 in the kurtosis. And instead of the count, multiply the count by the standard deviation cubic, and here raised to the power of 4. To get the excess kurtosis, subtract kurtosis from 3. After that, you can print the different features. And to plot the histogram, we will use the matplotlib. We created a figure. We created a bar chart using the bar function. We defined the range. So simply, whether you use any b.arrange min to max, or simply you can use the range variable here. They are similar. And the y-axis is the histogram to D. As we mentioned, it stores the frequencies. We added the title, X label, Y label, and we mentioned the aim of title layout to adjust the layout and the spacing. Then we saved the figure, displayed it, and deleted the figure and closed it. If you executed the code, you will get the following values, which are similar to what we got using the hand calculations and the corresponding histogram. So simply, you can test yourself by updating this matrix, calculate it using hand calculations, and validate your results using the script. The next task is to apply the same script, but instead of defining the matrix manually, we need to do that on the ROI or the 2D image. As we mentioned, we have image and mask, applied bitwise and to get the ROI, apply the bounding box to get the cropped ROI, and this is the regions that we need to extract the first order features from it. So simply, go to the force code, first order features for 2D. Here we defined the libraries that we need, and you will find here a custom helper functions file that's located here, and inside it I created a function called first order features 2D. So instead of writing the same code each time, I encapsulated it into a function that can be used later in upcoming scripts. So simply, I created the function with that name that accepts the image and the mask as arrays, and I defined also two values here, is norm for applying normalization, ignore zeros, and both of them are Boolean with default values of true, and we will mention the benefit of each of them after a while. In the code of the first order features 2D, I got image and mask, applied bitwise to get the ROI, applied the bounding reg to get the cropped version, then I added the features. And instead of using the matrix that we called here X and here X for minimum and the maximum, I used the name cropped, which is also a 2D array with the type unsigned integer and also a numpy array. I used the same code as you see here until I reach it to calculate the excess kurtosis. Instead of printing it, I stored it in a dictionary, and the dictionary consists of keys and values. I stored the key and the corresponding value for each feature. Then I returned two things, the results, which is the results that contain the features, and his2d to be used later if I needed it. And the his2d are the frequency of each pixel, as we mentioned. So I can use this function in any script by importing it. Here I imported all of the functions from the file, defined the basis for the image and segmentation, read them using grayscale, and then passed the case image and case segmentation to the function and got the first order features and the histogram. I defined here two statements. One is commented and one is not. Here I defined ignore zeros with true, and here I defined ignore zeros with false. What is the difference? We will mention it. But first, in the rest of the code, I printed the different features, and each feature is rounded to 4 decimal points. Then I got the minimum and the maximum, so I can display the distribution and store it. So if I executed the code based on the lever segmentation and the image, I will get this distribution. Here, I ignored the background by setting ignore zeros with true, and you will find here that the zero value has no corresponding values. What does zero mean here is the background. I don't need to calculate any features from the background, so each time I'm going to calculate the features, I will ignore the background by simply ignore the corresponding frequency of the zero. How we did that? Simply in the created function, I went to add this step. If the flag is true, simply skip the first element. So I got from the second element at index 1 until the end and stored it in the same variable and incremented the minimum value. So instead of starting from 0, it should start from 1. After ignoring the background or the zero values, now we have the distribution. Based on the skewness and the excess kurtosis, we can say it's positive. So we have a peaked distribution. It's negative as a skewness. So we have a distribution which is left skewed. What about normalization? Normalization means that we need to normalize the frequencies, and it's essential to normalize the features to avoid getting very large numbers. For example, at pixel 125 here, we have a very large number, which is around 1000. If we counted all of these values, we may reach a value of 100K or more. So we need to normalize to avoid getting large numbers, and this will help later in our classifier. Instead of dealing with different features with different ranges, some of them are small, some of them are very large. So simply normalize each feature, and the classifier will not focus now on the different ranges, but on how to discriminate inside this unified range. So if you apply normalization, you will reach a count of 1. And this is a validation that the total sum of the distribution reached to 1. And how we did that? Simply in the code, after getting the frequency, divide it by the sum of the frequency. So it will divide each frequency by the total sum, and hence it will reach a count of 1. So instead of dealing with a numeric value, it will be converted to a probability. What about if I included the background? Look here, the difference between including the background and excluding it. By ignoring or excluding the background, we saw the distribution. By including the background, as you see, 0 reached to around 25K as a value, while the rest of the distribution is flattened. If you depended on that approach, all of the figures or most of it will look like the same, flattened, because the 0 will contain the highest frequency or the probability. Also, it will be reflected in the excess kurtosis. Instead of being positive as a large peak, it will be converted to a flattened distribution. The third task here is that we need to apply the first order features on the volume. Simply, as the first order features deal with the pixels regardless the relationship between the neighbors, so simply calculate the first order feature for each image individually and then find the mean of the features. This is an approach. There is another approach that we didn't follow here in our lecture, is to deal with the volume as a big matrix or a big array and calculate the features from this big array. To follow the first approach, let's go to first order features for 3D. Here we imported the libraries and the helper function from this file. We defined the volume paths and we created a summary list here that will include the features for each image that we will later store it in case if we need it, and based on this summary we can determine the mean values of each feature. Now we have slices. We will get the files. We will loop on each file in the slices and the corresponding masks, get the file and get the corresponding path for the segmentation, double check that they are existing, both of them, read the images as grayscale, just in case if the images doesn't contain any mask, ignore that image. So continue here will skip the iteration and skip that image if the sum of the segmentation is 0, and this means that the whole image is dark. As you see here, some images doesn't contain any segmentation, while others contain. Based on the image and segmentation, apply the first order features, and we didn't include here the two other variables because by default they are true, and we need them to be true to ignore the background or zeros and to normalize it. We will get the results and store the image file name into it because this is a dictionary. We will assign a new key here is the image with the corresponding image file and append the results in the summary list, which we defined at the beginning of the code. It will start and loop on each image that contains mask and calculate the features from it. After that, we will use pandas, and pandas is a package which we imported here, which is useful for data manipulation and saving. So we'll use pandas here to save the summary as a CSV file that can be used later for interpretation or processing or any tasks. And also you can open the CSV file using Microsoft Excel. To store the summary as a CSV, we will convert it to a data frame. We will get the data frame and use the function to CSV, define the path, and here we defined index equals to false because by default index equals to true, and here it will add a column at the beginning with the index starting from 0 until the end, and we don't need that, so we'll ignore that by setting index equals to false. After that, we printed the mean of the features. As you see here, we got the values by simply looping on each key from the features and got the mean and rounded the mean to 4 decimal points. So when you execute the code, you can get numbers like that. We have 29 images, and these are the mean values. This is the mean excess kurtosis, and this means that the whole volume is flattened and skewness with negative value, which means it's left skewed. Also, in the stored file, you can open it and interpret each file. You will find here the image and the name of it as we stored it here. So for slice 45, these are the values. If you look and differentiate between 45 and 46 here, which belong to the same volume, 45 has an excess kurtosis with a negative value 0.4, while 46 is negative 1.6, and this means that the distribution of the slice 46 is more flattened than 45. However, the overall mean value for the excess kurtosis, as we mentioned here, is also flattened. While in 69, it has a small peak because it's positive. The same for 66. So simply, you have this file which is stored for each slice. Now you can interpret each image in the slice and also interpret the whole volume from the mean values. So how to reach the code? You will find the link in the Blackboard, or you can easily go to that link, and to download the files, you can press on code and download, or simply if you know GitHub, you can clone that repo. So in this lecture, we recapped the AI workflow in Radiomics. Then we went through the meaning of an image, volume, ROI, cropped ROI, mask, and how to apply bitwise AND to get the cropped ROI, until we reach the second part of the lecture, which is extracting the features. We compared between first order, second order, and higher order features. We started with the first order features, and we mentioned that it targets the distribution and pixel intensities rather than dealing with the relationships, which will be later be incorporated with the second order and higher order features. Then we cover multiple features such as mean, kurtosis, skewness, and standard deviation, interpreted each of them, and known the meaning behind these features. We applied that using hand calculations and scripts for simple metrics, images, and volumes.